It is the size of a fingernail, made of common sand, yet it is more valuable than gold, oil, or diamonds. It is the invisible architect of your reality, from the smartphone in your pocket to the guidance systems of intercontinental missiles. Without it, the 21st century simply doesn't exist. Today, we're peeling back the layers of the most complex manufacturing process in human history to understand the semiconductor, the invisible engine that powers everything you touch. To understand the modern world, you have to stop looking at the buildings or the roads and start looking at the silicon. The story of the semiconductor is not just a story of engineering. It is a story of how we learned to manipulate the fundamental laws of physics to store human thought. It began in 1947 at Bell Labs. John Bardeen, Walter Brattain, and William Shockley were tasked with solving a problem that was plaguing the telephone network: vacuum tubes. Vacuum tubes were hot, fragile, and inefficient. They burned out constantly. The team wanted a solid-state device that could perform the same function, switching and amplifying electrical signals without the heat and the glass. When they created the first point-contact transistor, the world didn't notice. It looked like a clumsy experiment on a workbench. But they had just invented the on and off switch for the digital age. By the 1950s, this tiny device had replaced the vacuum tube, paving the way for the integrated circuit. The genius of the integrated circuit, co-invented by Jack Kilby and Robert Noyce, was the realization that you didn't need to solder individual transistors together. You could etch them directly onto a single slice of semiconductor material. This was the birth of the chip. Suddenly, the complexity of a computer didn't have to grow linearly with the number of parts. We could pack millions, then billions of components onto a single die. This is what we call Moore's Law. Gordon Moore, a co-founder of Intel, observed that the number of transistors on a chip doubles approximately every 2 years. For 50 years, this hasn't just been a trend. It has been the heartbeat of the global economy. But let's get into the how. How do we actually make these things? It's arguably the most difficult feat of manufacturing on Earth. It starts with sand, specifically silica. We purify this into hyperpure ingots, 99.999999% pure. A single impurity the size of a virus can ruin an entire wafer. We slice these ingots into wafers thinner than paper. Then we use something called photolithography. Imagine using a flashlight to print a street map onto a surface, but the map is so small that the lines are measured in nanometers. We use extreme ultraviolet light so energetic it can only exist in a vacuum, to etch circuitry into the silicon. This is done inside fabs, which are the cleanest environments ever created. A hospital operating room is a pigsty compared to a semiconductor clean room. Then there's the supply chain. This is where the story shifts from engineering to geopolitics. Because the process is so incredibly difficult, the expertise has specialized. A company like ASML in the Netherlands is the only company on Earth that makes the EUV machines capable of etching sub-7 nanometer chips. TSMC in Taiwan handles the actual fabrication for companies like Apple, NVIDIA, and AMD. NVIDIA designs the architecture, but they don't own the machines that build them. The world's economy is essentially a giant spiderweb relying on a handful of specialized nodes. If one node breaks, due to an earthquake in Taiwan or a geopolitical blockade, the entire global output of cars, medical devices, and AI models grinds to a halt. And that leads us to where we are today, the AI era. We have reached a point where the speed of silicon is no longer just about running spreadsheets faster. It is about enabling neural networks to learn. The chips we see today, like NVIDIA's H100s, are no longer just CPUs. They are massive arrays of parallel processing power, designed specifically to perform the matrix multiplications that underpin large language models. We are building digital brains, and we are limited only by how many transistors we can pack into a square centimeter before physics pushes back. As we move below 3 nanometers, we are dealing with quantum tunneling, where electrons literally jump through the walls of our circuits because they are so small, they behave more like waves than particles. We are fighting the laws of nature itself to keep this progress going. The story of the semiconductor is a cautionary tale about how fragile our advancement really is. We have built a world that requires a level of precision we barely understand, managed by a supply chain that requires total global stability. As we look to the future, to quantum computing and photonics, we have to remember that this isn't just about faster iPhones. It's about the foundational layer of human capability. When we talk about the chip, we are talking about the medium through which human intelligence is now expressed. If you enjoyed this deep dive into the invisible world of silicon, make sure to hit that subscribe button and leave a review. We release these breakdowns every week to help you understand the invisible forces shaping our future. I'm your host, and I'll see you in the next one.